Hi there, Ken the Metal Professor here with another video to answer a few questions recently posted somewhere on Math Reddit. We're going to look at an implicit differentiation question, a polynomial division question, and a question about triple integral over a three-dimensional region, which is better solved by changing the coordinate system. And if I look a little bit distracted at the moment, it's because this thing was under my desk pawing at me to get attention. Okay, go away now. Nope, go down. Get away. I should edit this out, but, you know, he's cute, so he needs screen time. So let's tackle the implicit differentiation question first. The other two, I'm going to use a writing tablet, not slides, because in particular, I didn't want to create slides for a three-dimensional region. That would take way too long. So implicit differentiation. This solution is going to work all the way through to the end, so I'm kind of giving it away, but these questions have been posted for about a day, if not more, so by now it should be fair to just kind of give it up, where a lot of the people much smarter than me that have replied already in these threads have given really good hints. So we're going to look for the derivative term dy dx for an implicitly written function. Now remember, implicitly written functions are just functions that aren't pre-solved for y. Functions are a relationship between the dependent and independent variable. Like in a hotel, when you check in and there's that little that paper strap around the toilet that says sanitized for your protection. 99% of the time in calculus, your functions are already sanitized for your protection, meaning they're already solved in terms of the dependent variable. They're written y equals. Okay, well, that's not necessary. Relationships can be written all sorts of ways, and in particular, this relationship, 3 cosine of xy equals 5x plus 4y, does pose a relationship between x and y, but it cannot be algebraically solved for y. Now, it would still represent a curve in two-dimensional space. There would still be tangent lines along that curve. There would still be rate of change of y with respect to x. And so that relationship, that rate of change of y with respect to x, is what we're going to draw out from this. The way this works is that we just ask for the derivative with respect to x of both sides. This is exactly what you do with a function that is already pre-solved for y. You are finding d over dx of both sides. It's just that that left side, if it's already y equals, then the dy dx just falls into your lap. Here, we're going to have to dig it out a bit. Okay, so between these two sides, the right side is easier, so let's take care of that. I'm going to develop it excruciatingly slowly. So we're looking for the derivative with respect to x of 5x plus 4y. We can distribute the derivative operator. We can factor out constants because the derivative is a linear operator, which means you can distribute it across addition and you can factor out constants. The two derivatives that we've isolated are both easy. The derivative with respect to x of x is just 1. And this derivative with respect to x of y, well, we don't know what that is. And in fact, that's the whole point of the problem. That is dy dx, which is the very thing we're looking for. So dy dx does not appear as explicitly solved for as in other problems. It shows up and then we've got to dig for it. Altogether, the derivative with respect to x of 5x plus 4y is 5 plus 4 dy dx. Now let's go to that left-hand side. Okay, this requires both a chain rule and a product rule in order to dig out the dy dx. Because first of all, hopefully you recognize that 3 can get factored out. Right, that's pretty easy. We're going to have to look for the derivative of the cosine of xy. Now remember, in general, because of the chain rule, the derivative of the cosine of anything is going to be minus the sine of that thing times the derivative of that thing. In our problem, that thing is xy. When we ask for the derivative of x times y, we have to remember that y is a function of x. This is something just repeat to yourself over and over. Y is a function of x, and it must be treated accordingly. So when we get to the point here where we're going to look for the derivative with respect of xy, well, x is a function of x, and y is a function of x. This is one function of x times another function of x. What rule gets used to evaluate that derivative? Well, the product rule. Okay, so remember that y is a function of x, and you have to treat it accordingly. Here's how that works. The derivative with respect to x of x times y. Product rule says each piece gets its turn under the derivative operation while the other one just sits there twiddling its thumbs. So here the x is standing by while we find the derivative with respect to x of y, and then in the second term, the y is just sitting there minding its own business while we do the derivative of x. The derivative of x is 1, and like on the previous piece of this d over dx of y, well, we don't know what it is. That's the whole point. It has shown up here, the dy dx, and so when we put everything back together again, we're going to end up solving for it. This is the net result of that left-hand side derivative. So we just did the derivative with respect to x of x times y in preparation for placing it here. Now we're going to expand the full derivative of that cosine. So here's the 3 that's been factored out. The derivative of cosine is minus sine of what? Well, of x times y, and then times the derivative of x times y, which we just saw was this, and then I've multiplied through by that 3 sine xy. Normally, we wouldn't want to multiply things through like that. It's already nice when it's factored. However, we're going to have to solve for dy dx, so I've gotten it in its own little term. So let's reassemble. Hit the reset button. We took the derivative of both sides of the original function. We developed the derivative of the right side first. Here's the development of the left side that we just finished. And now we see 2 dy dx's. So let's solve for them. Let's gather them together by subtracting 4 dy dx to the left and then adding this term with no dy dx over to the right. Now let's factor off the dy dx and also factor out a minus sign. And now we can solve for dy dx by dividing both sides by minus 1 and then dividing both sides by that mess. And there you go. Okay. So the overall strategy for implicit differentiation, where your x's and y's are jumbled up and it's either inconvenient or impossible to explicitly solve for y. To do some planning ahead, you take your expression and you count how many y's you see, because that's the number of places that you're going to come up with a dy dx when you're running the derivative. And in fact, that can help you put some red flags in there for yourself. Let me just go back to the very beginning of this real quick. Right, we're finding dy dx for this function. Well, how many y's are there? 1, 2, which means we expect to come across 2 instances of dy dx as we're evaluating the derivatives of both sides. And when we put it all back together, we did, right? We got 1 dy dx on the left and 1 on the right. Now, generally speaking, whatever your relationship is, count the y's. That's how many dy dx's you should expect to see. So if your functional relationship, maybe there's 3 y's peppered around in different places, and you take the derivative of both sides, you only come up with 2 dy dx's, something's wrong. Or if there's 4 y's altogether, but you come back with 5 dy dx's, something's wrong. So that gives you a little red flag as you're in progress with your solution. But anyway, just like we did in the example, take your original expression, ask for the derivative of both sides with respect to x, find the derivatives of these as usual, meaning remember that y is a function of x and it has to be treated accordingly. So if we're asking for the derivative of x times y, that's one function of x, x times another function of x, y, which means we need the product rule. If it's e to the y, well, y is a function of x, and so it has to be treated accordingly. So the derivative of e to the y isn't just e to the y, it's e to the y times dy dx because of the chain rule, and so on. So be alert for the need to use product, quotient, or chain rules in that process. And eventually, you're just going to collect all your terms where dy dx is bubbled up. You know how many spots to look for when you start the problem before you do any work. You know how many dy dx's you're going to see. And then you solve for dy dx. And that is the overall story of implicit differentiation. Okay, moving on to something a little simpler, or more aggravating, depending on whether you're good with it or not. It was just a question about polynomial division, and some of the people I've been working with have been doing this, so it's fresh in my mind. So let's do another example. I didn't want to lay out a division format on these slides because that would be aggravating. I should probably learn how to do it and then save a template, but I haven't done that yet. So with my bad handwriting, here we go. So this is how polynomial division works out. It's just like long division, but with more clutter. So we're dividing the original polynomial by the quantity x plus 5. We just look at the lead terms to start with, and we ask the same questions as when we're doing regular long division. How many times does x go into x cubed? Well, it goes in x squared times, because x squared times x is equal to x cubed. And in fact, we take this x squared and we multiply by x plus 5. We get x cubed plus 5x squared. And then we subtract that result from the original expression. The x cubes are gone. 4x squared minus 5x squared is negative x squared. And then we can drop these two terms down just to keep things intact. Repeat. X goes into negative x squared minus x times, because minus x times x is negative x squared. So do that. Negative x times x plus 5 becomes negative x squared minus 5x. Subtract. The negative x squareds are gone. Negative x minus negative 5x is negative x plus 5x, or 4x. Bring down that 25. Last time, how many times does x go into 4x? Well, 4. 4 times x plus 5 is 4x plus 20. We subtract. Now this becomes negative 45 altogether. X cannot go into negative 45 anymore, which means now we've reached our remainder, negative 45 over x plus 5. And so this cubic polynomial divided by x plus 5 results in this. Okay, now there is a quicker way to do it, although it requires more memorization of an algorithm. This version of the problem, if you remember how to do regular long division, you can use that format to do polynomial division. You see everything that's happening. And it's very simple to go back and check for errors if you decide that you've made some, which hopefully I haven't. I haven't checked my work. Okay. But there's also synthetic division, and here's how that works. My polynomial was x cubed plus 4x squared minus x minus 25. Let me double check. Yes. Okay, and we're dividing that by x plus 5. Now, synthetic division says take the coefficients of your terms. There's a 1, a 4, a negative 1, and a negative 25. And then put a number in a little bucket over here to the left, where we get that number by matching the divisor that we have, the linear divisor, with a template x minus b. Why is it that template? Whole other story. This is an algorithm. It's something you can do even if you don't understand how it works. But basically what it does is it's going to take this version of the problem and realize, as long as we agreed that the polynomials are written in descending order, cube, squared, linear, constant, we don't need to see the x's, right? That's just noise. All the good stuff is in the coefficients. And so synthetic division just takes that story and compresses it. but you have to remember the algorithm. If we match up x plus 5 to x minus b, then b is negative 5, and that's what goes here. Okay, and here's the process of synthetic division. Ready, set, go. Drop the leading number, multiply, put the result here. This time we add. Remember, in long division we were subtracting, now we're going to add. 4 plus negative 5 is negative 1. Multiply, add, multiply, add. And then, again, remember that these are coefficients. There's a constant. There's the linear term. There's, well, it's got to be the squared term. So the net result is going to be x squared minus x plus 4x. And then this is the remainder term, minus 45 over x plus 5. So that's the result again, which better be the same thing as we got back there. It works. Okay. Last problem. This is quite a jump from pre-calculus polynomial division to Calc 3, multivariable calculus triple integrals. Okay, so what I've done here is I've copied in or typed in the phrasing of the problem as posed by the user, but it was a photograph or a scan, one of those two, of the actual assignment document. Whether it was a page from a book or a handout, I don't know, but it was the document that contained this question. It was not the user writing the problem down. He was showing us, or she was showing us the original source. There has to be a typo in this. This cannot be the order of the differentials for this triple integral, and here's why. We integrate multiple integrals from the inside out. So if dx is the first one we encounter, we're going to have to integrate, find the antiderivative of this thing with respect to x. Now, whether or not that's even possible is a whole other story. Let's say we can do it. Then we're going to plug in the endpoints of integration from this innermost integral back in for instances of x, which means we've just tried to integrate x away, and we're about to reintroduce x's. And then as we move out to this integral, we're going to introduce more x's, and then we get out here, we're still going to have x's left over. This integration is supposed to resolve to a value. This integral is actually measuring the volume of a three-dimensional region. The answer has to be a number. This, as posed, is going to produce a soup of x's with values floating around with it. Okay, so this has to be a typo. Again, not on the user that posted this, but this is on the person who created the document that contained the problem. Now, I'm going to assume that this is a standard triple integral problem, and the ordering of the differential should be dz, dy, dx, meaning we're going to integrate with respect to z first, and then with respect to y, and then with respect to x. Okay, now, given that that's fixed, if you try to find the antiderivative of this thing with respect to z, good luck. U substitution isn't going to work. I don't think trig substitution is going to work. I mean, maybe it would in a weird way, but it would certainly be at least a hassle. The geometry of this problem suggests that we should change our coordinate system. When you're taking multivariable calculus, you've been doing rectangular coordinates all your life. By the time you get to the end of single variable calculus, you've probably been introduced to polar coordinates, and then you get to multivariable calculus, and then you get cylindrical coordinates and spherical coordinates, and you say, oh my gosh, these things are terrible. Why do we have to know all these coordinate systems? Well, one of the reasons is that they will actually make your life easier. Doing this integral as posed, no thank you. But you're going to see that if we change our coordinate systems, the resulting integration is going to be a snap. Because we're going to turn all of those nasty limits of integration into mostly either constants or simpler expressions. The function that's being integrated is going to be a little bit simpler and will actually provide an integrand that we can handle with just a mere substitution. Okay, so here's what we're going to do. We are going to understand the geometry that's being dictated here, and then we're going to pick an appropriate coordinate system and then solve the problem. Actually, I'm not going to solve it all the way through. I'm going to do the conversion and then leave the triple integral as practice for the viewer. But it will be certainly a lot simpler than this. Okay, so first of all, let's understand the region of this integration by examining the limits of integration. And again, presuming that the order of integration was supposed to be z then y then x. So this is telling us, this middle integral, or the innermost integral, is telling us that our region of integration is bounded below by the surface z equals x squared plus y squared. I'm writing it down. You can't see it yet, but I'll get there. Okay, so these are the fundamental surfaces which start delineating this region. This is a cone. This is a plane. Here's what they look like. There's my cone. I draw the cone before I worry about my axes. Okay, so three-dimensional coordinate system, like so. So this is z equals square root of x squared plus y squared. And let's just say that this is z equals 1. So the limits of integration are telling us to look above the cone but below the plane z equals 1. The other two limits of integration are telling us what shadow of this region in the xy plane we want to have coverage from. This is telling us that the y limits are starting at 0 and going to, this is a semicircle, hopefully you recognize that, and x is just going from 0 to 1. Because x and y are both always positive from these limits, we are only worried about the first quadrant. So when we come back to my terrible diagram here, I'm going to take the xy plane and I'm going to flip it up so we can see it. Those limits of integration tell us that we're only interested in that portion of the xy plane, which means that we are only interested in a fourth of the cone up here on top. The portion of the region between the cone and the horizontal plane that's above the first quadrant. So another way to describe this triple integral is to say, let's evaluate the integral of this nasty function in a three-dimensional region bounded below by this cone, z equals square root of x squared plus y squared, above by the plane z equals 1, and in the first quadrant or octant only. Okay? That's what we're after. Now, because of the function and the limits that are given, it's actually going to be more convenient than leaving it in rectangular coordinates to do this problem in cylindrical coordinates. The integrand function with this square root term, that looks an awful lot like the equation of a hemisphere. So you might think spherical coordinates. However, when you get to these limits, the fact that the upper limit on z, as we're assuming, tells us that the top, let me get back to my window here, the top surface of this integration region is a flat surface. Spherical coordinates do not work well there because the radial coordinate in spherical coordinates is the distance from the origin, and in this region we have different distances from the origin depending on where we're hitting that top plane. Okay, so spherical coordinates isn't going to be very convenient. We're going to do cylindrical coordinates. Now, in cylindrical coordinates, this cone is also known as z equals r. The plane, well, it is what it is. I'm going to write one more thing on this messy slide and then switch to new one. We're going to be using cylindrical coordinates r, theta, z. The usages of theta and r are not universal. Some people will use rho for the radial coordinate, maybe phi for the angular coordinate. It is what it is. I'm going to use r, theta, and z. So if I come to a fresh page and I say, look, what we wanted was the integration of that messy function in a three-dimensional region, which is above the unit quarter circle in the first quadrant, underneath is, above the cone, but below that plane. This cone is z equals r. This plane is z equals 1 in cylindrical coordinates. And then down here in the xy plane, remember we are over that quarter circle. It's the unit circle because we had a radius of 1. The bounds of this in cylindrical coordinates, which in 2 dimensions are just polar coordinates, r goes from 0 to 1. Theta goes from 0 to pi over 2. That's our radial coordinate. Okay. Now, I'm assuming some familiarity here with cylindrical coordinates. But if I go back to the original problem here, I can now reset the limits of integration. And I'm going to write something before you can see it. I'm just getting ready here. The lower limit of integration is z equals r. The upper integration is z equals 1. And then, assuming r is the middle integral and theta is the outer integral, in cylindrical coordinates, these limits are going to be 0 to 1 and 0 to pi over 2. The total differential here, the volume differential, what would generically be called dv, in rectangular coordinates, dz, dy, dx. In polar coordinates, cylindrical coordinates, it's r dz, dr, d theta. And what about this function? Well, again, this is where I'm presuming familiarity with cylindrical coordinates. The x squared plus y squared is just r squared. The z squared just is what it is. So 1 over square root of r squared plus z squared. Sorry, my handwriting on this tablet is horrible. But if I squish the inner part, I can tidy this up a little bit. Notice that 5 of my 6 limits of integration are constants. This lower limit is simply z equals r. The function, along with this extra r that's come in through my dv differential, has now given me something that when I ask for an antiderivative with respect to z, it's going to be a little better than it might have been before, not a whole lot. But at this point, I wouldn't recommend doing this by hand. I would still go do an integration engine. So I'm going to stop here. However, what I wanted to show this problem for was the practice of taking a nasty rectangular coordinate triple integral, fixing what was probably a typo right there, and then recognizing that we can generate a relatively more streamlined version of this result. This first integration with the z and the square root of z squared underneath, that would require a trigonometric substitution, very likely. So to do this by hand would just be horrible. But this is much more compact and understandable than it was before, at least to me. So I like these problems. That's why I picked it. I hope it helped, even though it's not finished. Zoe, the calculus dog, is excited about it. You can hear her barking. She knows when I'm making videos.